All right. Okay, homework's due today. Make sure you're getting that turned in. That was at page 701. Make sure that's in. You need a calculator today. You need your notes for sure. At some point, we're gonna bring up the Chromebook thing today. Goal today is to talk about arcs that we introed yesterday, but to also go to the more in-depth stuff and talk about a couple of properties that are involved. So I want to really focus on what arc length is to begin with, and then we'll get to the actual other things because there's a couple other postulates and things that that we're going to need. So take those out. So have your notes out and all that good stuff. So we'll kind of walk through it here. Let me get to the major parts here. All right. All right. First thing, let's go over what section we're in. We're in obviously section 10.2, which yesterday I referred to as central angles and arc measure. Angles and arc measure. Okay, or arc length, I think I called it. The goal today is to really talk about the relationship of these two. So first thing, let's just review what what central angles are. We'll review that. We'll make sure that that you're comfortable with like the main property that you should know about circles, which I think most people do. In fact, let's just start in on that right now. Let's just start with that first obvious property that most people know is like the definition of a circle, basically. That's here's my circle.
Nice circle.
Let's call it C for the center. Let's have a couple radii coming off of it. So we have a couple different angles. Let's call this angle 1, angle 2, and we'll call this one over here angle 3. That's the big one. We can even give it letters. Alright, what do we got? We got A, B, and D. And we'll put a letter over here somewhere. Let's put E. Oop. D. There we go. Okay, so here's my circle. The main property I want you to know, and this is one of the things that comes back to just central angles. Central angles are angles that are at the center of a circle. It's obvious, like most people have that common sense in their head. But the first thing you need to know about a circle is that you can actually add those central angles together. So if you add angles 1, 2, and 3, so this is angle 1, that's angle 2, angle 3, that you're actually going to get a specific number for every circle. And what does a circle have to add up to be? 360. Okay, so that's the idea. I think we even used that fact yesterday. That's one of the main properties of circles. It's the big one, right? It's the one that actually explains why certain angles work out the way that they are. Now, whatever angle 1, 2, and 3 is, I can make any numbers I want. You can always find the one that's missing because of it, right? So let's say I was missing angle 3, like I just didn't have that. This is my question mark, like how big is that angle? But I have the other two. Let's say that this one is, I don't know, let's say this is 70 degrees and this is 40. Okay, we'll put a little degree symbol on. Now we can find the one that's missing because of that same concept, right? So if you have the 70 and 40, you can plug those in. I don't even care where they go. If 1 and 2, I don't even care if you put them in the right spots. But this is my mystery angle, but you know they should add up to be 360 anyway. Right, so this is going to add up to be, what, 110? And if you subtract that across, what is that, 250? If I subtract that across? And that's this angle over here. This should be 250. And that makes sense, right? It was more than 180 degrees. When you look at the picture, it was huge, right? 180 straight across. So it was definitely a reflex angle. It's past 180, past straight. But the other thing that gives it away is that these only made 110. So it is an obtuse angle. It's actually a reflex, right? Questions with the first basic property of math, right? About a circle. It's not really even a property. It's just kind of like a definition of a circle that they always have to sum to be 360, no matter what the circle is. I can guarantee, like, the stuff we're going to do next week, not this week, but next week, we're going to do problems like this where you're missing certain angles and you can find them. The big thing that will help is doing things like this. Knowing that when they draw this line straight across, that makes a diameter. Usually they have it marked. So now you can actually find both of these angles separately. Like, I know that the big angle that we said was angle 3 was 250, but this is 180, And now you can find this mystery angle over here as well. Which, what is it, 70? Something like that. The reason why these have to add up to be 180. So if that's 110, that adds with 70 to make 180. Because each half of the circle should make 180. Those are called semicircles, right? Half of a circle. Questions about the central angle stuff? I know we didn't really stress that yesterday. I just kind of figured you knew it, which you did. But that's central angles. Now, tying that perfectly into the new stuff today, we need to talk about arc length. And this is the part that we really hammered down yesterday. We had 3 types of arc length. The 3 words that I wanted you to know. Number 1 was a minor arc. Anyone remember what a minor arc is?
Shortest distance.
Yeah.
A to B.
Yeah, A to B or B to D. It's like the shortest distance. You have to travel along the circle. I don't know if I stressed it yesterday, like, because some people, if they think shortest distance, they're like, just got the middle. No, you got to travel along the circle itself. So the actual arc is this. So that's a good example, A to B. We talked about, the notation for that you write 2 letters and you put a little bubble above it. That notation right there means the actual length. So, I don't know, let's say that it was, say that's 17 inches, I have no idea. Let's say it's 17 inches. Well, that's what this represents. It represents the actual length of like the pie crust, the pizza crust. Now, if you put a little M out front, what did that mean?
70.
Yeah, 70 degrees. It's the angle when they put the M. I know that seems a little weird. They just want to differentiate, are they talking about the angle or the actual like length of the wall? So M means the actual measure of the angle. All right, questions, comments about notation stuff, about arcs and all that? They really don't talk about anything else in there, but we're good with minor arc, the small angles. Okay, then we talked about the bigger ones, which one of the categories we had was a major arc. This is the second category I think we went into yesterday. A major arc, that's big. So on this picture, can somebody give me an example of a major arc? Say it again?
A to B, but.
Okay, yeah, A to B, but going like the long way around, right? So when you go the long way around, so now we're not doing the 17 inches, we're going this way. You can start with any point you want, so I'm going to start with A. We'll go A to B, right? So you're going to go A to B, right? B is going to be the last. But you have to have at least one letter in the middle that you're going to hit. So if I'm going A to B the long way, what's one of the letters I'll hit? E? Yeah, that works. Put E in the middle. You only have to use 3 letters, not 4. Just use 3. Question?
So if it was like B to B, would you go around, so the opposite way the A is going, to go to B?
So if I wanted to go E to B, this potentially could be, if I'm going this way, that could be potentially a minor. But if I want to go major, yeah, go this way. So E, A, B, that'll work. Question?
What if they're opposite each other? Like what if it's D and then like directly above D's?
Oh, where it's like a perfect, the perfect straight across. Yep, that's the last one, right? That is the semicircle. That's where it's perfectly on the other side. So semicircle is perfectly half the circle. So like what we're saying here is we're going to put E. Let's put it over here, right there. Is that what you're asking? Okay. So that is a semicircle. It's perfectly half. And in fact, I had another semicircle over here, but let's just say, let's get rid of this one. It's no good. All right, so if we put that over there, E to D is a semicircle. Now this is a diameter going through the middle, but how you actually write semicircles, you still have to use 3 letters because it's not minor. It's like, it's kind of going the long way around because you're going more than, and you're going halfway or more. So when you go halfway or more, you have to use 3 letters. So if I want to go E to D, let's say, I'll go E, A, D. Let's just write that, E, A, D. And that's going exactly halfway around, but you still have to use 3 letters. The minors use 2, but everything else use 3. Now if I had to go the other way, because I know a lot of you will ask, like, what if you went this way? They have to put at least a point over here somewhere. They have to have a 3rd point to put. So E, F, D, that'd be the same thing. Now if I put an M out front, what does that mean?
Measure of.
Measure. So you'd have to actually measure it. So E, A, B, I think we said, oh geez, what is that? 290? It's 290, I think. A to E to B. Going this way. I think that's 290. Question?
What if
E and F weren't there, who did A to D, like, the long way around? Is that-
Oh, if these weren't here,
Yeah.
and I had to go the long way, you'll have to fill in a dot yourself. You'll have to just make up one. Yeah, they have to at least give you 3, so, if they don't, you'll have to make up one to put in the middle of it. So, yeah, good question, that's a really good question. So, but yeah, so, if it's minor, 2, if it's major, you have to use 3, and you might have to make up 1. I won't ever do that to you, you'll have enough that you need. But, how I explain the 290 idea, it's going E to, oh god, I erased a letter. Alright, E, A, E, B, that's going this way to B, that's the long way, because I use 3 letters. And why it's 290, it's doing the full 360, but I'm taking away that piece, yeah, the 70. And that's why it's 290. Okay, so you gotta think kind of like reverse that problem around. How do I get, the big angles? So, the easiest way is taking 360 and subtracting chunks out of it. Or maybe you just knew what these pieces were. Like this is 180, so you know that was 70. So you could add the 70 and 180 and 40 together. Maybe that's the best way you could do it. Okay, questions with any of the 3 that we talked about yesterday? Okay, new part today. I want to get to the new stuff. I want to talk about how do they directly relate to each other? The arc versus the angle itself. I hinted at it yesterday, but I do want to show you because I think it's really cool, especially what you can do with it. So let me start the camera here and we'll try it. All right. So let's do one of these. Now let's go to new picture. We'll go ahead and erase. Okay. All right. So let's make up a circle here. And now this is the part where we get to make up our own number. I need a radius number.
12.
12. Jeez, weird. All right, 12. Feet, inches, centimeters, yards.
3. Feet.
Feet. Okay, feet. All right, 3 feet. That's a radius. It's very weird. You guys want to sync together. All right. So the radius is 12. What we're gonna do is I'm gonna show you that if you make a central angle right in the middle, right off that radius, we can actually find the path that you took along this circle, like how far you traveled, knowing that my radius is 12. And it actually does look almost like 12, almost a foot. So let's make up a number. So now this is gonna get weird if you guys guess the same number. I need an angle like that you're gonna open up.
8. What?
Let's go 89. Okay, let's do that. I'll mix the 2 numbers together. So, all right, so we're gonna say 89 degrees. Okay, it's big. It's almost an L shape. It's pretty close, okay? And I wanna know that distance right there, like that they actually traveled on the pie crust. So maybe it's like a tire, like a wheel, and it's rolling. So if you had it, here's the idea. So this is the point on the ground, and you rolled forward, so this is moving this way, right? So it's rolling, and eventually it gets to this point, right? That's what I'm looking for. So I'm looking at how far did you actually travel down the road before it actually touched again. That's what I'm looking for. And that's that number right there. So it's like a linear distance, but it's on a curve. There's a weird little formula that we have to actually calculate it. In your book, I don't know if it even has it as a theorem. No, it's just a concept. It's just like this. They say it's an extra property, basically, but it's actually really helpful, especially in like pre-calc. So here's the formula. Let me give it to you. It's really straightforward. It's really easy. Here it is. This is what they have. And I like to write down that formula. It's the simplest little formula in the world. S equals r theta. Theta is a Greek letter. It means an angle. S is arc length. I don't know why they use S. I would have used A, but I guess they don't want to confuse it with area. So in fact, let me just write those letters down. So S means the arc length, the actual distance you're going to travel. R is the radius of your circle. And theta, which is pronounced theta, that is your angle. Now here's the stipulation. That's theta, your angle. The angle is not in degrees. It's in a different form of measurement. It's called radian angles. It's in a radian measure. let you write that word down. That is a brain concept you've never seen. I almost guarantee you've never seen that concept before. It's on the same lines to me. I always think of radians kind of like feet versus centimeters. It's like the US system of like measurement, we use feet and miles and stuff, versus like the metric system that uses centimeters and meters and kilometers and stuff, you get the idea. So it's just a different form of measurement. So it's just something that you may have never used before, but there's a way to like convert. It's a very simple calculation. The problem is explaining it for the first time, like the conversion. I can show you what the conversion is, which I'll do here in a minute. But actually explaining how it works is actually kind of difficult. It's really, this is the hardest part for people to understand, is this whole like, what is a radian? Like what, because most people know what a degree is. You guys have been programmed since like junior high days or even elementary days to know like a degree is, an angle, and then you can open it up and you get to like 90s an L shape and 180 straight line. Like you've been so programmed to know what those are that when you move to a different form of measurement, it's really hard to wrap your brain like what is a radian? Like what is 1 radian? What I can tell you, like just to clear up some stuff before you get like super confused. 1 radian, just so you have this like in your head. 1 radian measure, like if you're going to go an angle, that's roughly 57 degrees. It's roughly 57 degrees. So if you have like an idea of what 57 degrees looks like, that's 1 radian. Okay, so some people just need to see that. It just kind of alleviates like the mental fatigue trying to figure out, like wrapping their head around what we're talking about, what it is. I'm going to show you the conversion, and then then I'll show you kind of like how did they come up with that. That seems a little weird. I'm going to show you this. So, all right, let's do the quick conversion. So I can actually show you how do we do this problem. How do we find the pizza crust or the wheel? Like how far did we travel? So what you do is we got to take my 89 degrees, and we need to convert this. So we're going to convert into radians. We need to do that first. We have to convert it. How do you convert 89 degrees right away? This is what you do, and I know it's going to seem really weird. You're going to take 89 degrees, you're going to take it times pi, like the number pi, and you're going to divide by 180. So this, when you actually multiply that, that's your conversion. That will actually convert the 89 degrees into radians. So whatever this is as a number, that's radian angles now. It's radian measure. Now the weird part is radian doesn't have a little notation. It doesn't have like a little marker on it like degrees do. Degrees have that little like circle in the corner of it. Radians don't have that. It's just kind of blank. So whatever this number is, so if you had a calculator, you could type in 89 times pi divided by 180. It's some weird decimal. And then we can take that number and we can take it times the radius. Because if you're looking at that formula right there, you take S, which is my arc length. You have the radius, which is, in my case, what is that, the 12 feet you guys said earlier? The 12 feet times my angle, which is this thing, whatever this decimal is. If you multiply these, this will give me how many feet we just traveled along that circle. Now, just to give you an idea, just to wrap your head around this, because what was 1 radian I said earlier? 57 degrees. Are we going more than 57 degrees? Yeah, we're definitely going more than 57. So what I can tell you right now is this is the common sense you should be thinking of. If this is more than 57 degrees, that means this number on a calculator is more than 1 radian. It's like, it could be almost, it's not quite 2, it's like 1 point something radians.
5.5.
Right, what was that?
1.55.
Okay, 1.55, almost 1.5. Okay, so that's nice. So it's more than 1.5 radian. So how I know that, again, 57 degrees is about a radian. So this is more than 1 radian. So what that means to tell me, like in my head what I should be thinking of, is I'm taking a number that's a little bit bigger than 1 times 12. So I know that I'm actually traveling more than a foot without even using a calculator yet. I'm traveling more than 1 foot because, or I should say 12 feet, sorry, 12 feet. I'm traveling more than 12 feet. The reason being is that when you multiply a number times something that's bigger than 1, the number grows. So I'm going more than 12 feet. Sorry, I probably just confused it, that whole 1 foot idea. I thought it was 12 inches. So if you take this number times a number that's bigger than 1, it will grow. So I'm expecting this number, I don't know, 15, 16, 17, 18?
18.6.
Boom, okay, in that ballpark. Because it's gotta be big, it's bigger than 12, I know that. But tell me the number again?
18.6.
18.6 feet. That's big, if you think about it. That's a long distance. So okay, so we did the 12, so 18, this number here is 18.6, you said?
Yeah.
6 feet. I thought those were inches. I have to look back at the video. I think I assumed it was inches from the beginning. Alright, but 18.6 feet. That's how far you're traveling. Okay, now, does the number make sense? Yeah. That angle opening up is pretty big, so you're kind of rotating the tire pretty far. So it's the concept is, taking this, and then rotating it 89 degrees. So if I rotate 89 degrees, you're actually going, a long ways around that circle. Now, why we use this? Okay, because this will get to the point why I like this stuff so much. This concept, this little simple thing that we do here, this is actually what Google uses to calculate the distance you're going to travel from city to city. I'm not joking. This is the formula that Google uses. It's a stupidly easy formula. But this will actually tell you the distance from like Ventura to Garner on a road. Like the actual linear distance. Because the Earth is like a sphere, right? We're on a sphere, we're on a curved path. Even though, it looks flat, it's not. In fact, you can tell it's not because you don't actually see Ventura in the distance. It actually like curves with the Earth, so you're just seeing like the top of the buildings. It's really apparent when you go to Mason, like Clear Lake itself, and this is something I learned in high school and I thought it was the weirdest thing in the world. The Clear Lake water line itself, all the water in Clear Lake, is actually higher than the tallest building in Mason. Wrap your head around that. It's the weirdest thing I've ever heard of. The water in Clear Lake is taller than the highest building in Mason City. Because it's curved, right? The city's down. It's lower sea level from Clear Lake, which I think is really weird to think about. Yeah, weird. Question.
So for Google, do they use like your tires, or do they talk about the circle?
Okay, the circle's the Earth itself. It's the Earth itself. So their radius is a lot bigger than you think it is. So the radius they're thinking of on Google is the Earth's radius.
What is that?
It's 4,000 miles. So the radius there, it's like 3,996, something like that. That's roughly what it is. It's really big because the Earth is huge. It's really big, right? So when they're talking about like how to go from like Garner to Ventura, what they do is they use the lines of latitude and longitude to help you. So it makes like the little tick marks, and this is what a lot of people don't know, is that the lines of latitude and longitude, they're angles. That's all it is. It's an angle. So let me give you a cutout so you can actually see this, which I think is really kind of a cool concept. Then what we'll do is we'll pull up like the computer and we'll actually check if we're somewhat accurate. Okay, so I can actually show you that it does work. Okay, so we'll go north and south first because that's kind of easier on a map than picking cities that are really close together. We'll go like further distance. Let's go from like, let's say this is Garner here, and I'll draw a better picture than this here in a minute. This is Garner, Iowa, and we're gonna go down to like San Antonio, Texas. We're going long distance, not just Garner to Ventura. Okay, so San Antonio, that's really long. So the radius of the Earth, what did I say earlier?
3,000, 4,000.
4,000, we'll go 4,000, that's good. 4,000 miles, okay? 4,000 miles. Now, to find this number, to find the angle that we use, you just use the lines of latitude on a globe. So let me explain, and this is where my actual drawing is. On a globe, so here's the Earth, and that's the equator. Okay, the equator is considered a line of longitude, or line of latitude. This is latitude. How I always remember latitude, it kind of looks like a ladder. in the rungs of a ladder. That's how I always think of it. And so when you go up in the lines of latitude, what these rungs are, this is like 10 degrees, and this is 20 degrees, and this is 30 degrees. What those are, what those marks are, it's actually like if you took a weird snapshot of the Earth, like here's the core of the Earth, and here's the equator way over here, and now I'm looking like sliced through the Earth with like a sword or a knife, and so this is the molten lava, and this is the crust, the mandible, whatever you want to call it, and then you have the top layer. The angles, like 10 degrees, 20 degrees, it's doing this. That's what they're doing. So when you get to the North Pole, this is where the North Pole would be, that's perfectly 90 for latitude. I think for us, Iowa's like 43 degrees or something like that. So we're up here somewhere. So let me draw my really, really bad picture. So here's the United States. There's the United States, right? No other countries. Iowa's there, right? And then Texas is here. That's a really bad Texas, just go with it. And so what we're doing is we're finding like the difference there. So really all we need, because Garner and San Antonio are almost like perfectly like north and south of each other. They're almost like dead south of us. So the idea is that you can just use the latitude number to actually figure it out. You don't have to do any weird other calculations to do it. So if it's perfectly south, just use that latitude number. So if Ventura, or I should say Garner, is 43 degrees north, and obviously there's a ton of decimals that Google will give you for what latitude we are, and San Antonio's like, let's say it's 30 degrees north, the difference between us is 13. Now that's not accurate, I'll actually give you a real number here in a minute. But if that was 13 degrees difference between our latitudes, that's 13 degrees right here. That's your angle between the two cities. Does that make sense, like how you do it? And this is what Google does. That's why it was so important for Google to get like GPS satellites working before they released the Maps programs and they did their other things that they wanted. Because they wanted to make everything accurate. And so mapping the Earth was the first thing they had to do. And then from there, then they can come up with geographical maps you can use. And then the next thing is to map all the roads. And then once they have the roads, now that they can do autonomous vehicles. Because now they have everything mapped out correctly. That's why they start really small cities. So it's a weird progression. You can actually see why they do certain things when you look at the big picture of it. But this is one of the first things that they offered on Google when it first started. Like, geez, how many years ago was that? 96? Google hasn't been around very long, but yeah, it's like 96, 95, something like that. But anyway, let's actually find the number. So if you guys have a Chromebook, please, I need somebody to type in Google, I need the latitude of Garner, Iowa. That's all I need. So you can just type in latitude of Garner, Iowa. It'll probably tell you really big, it's 43 point something degrees north. I just need to know those numbers, because I want to find this number really, really accurate. This angle. So I need Garner, Iowa. So if somebody has a Chromebook, do some web searching, search the Google machine, and let's see what we get.
43.0123 north.
Oh man, that's really accurate. 43 point what?
1023
1023
north.
degrees north. Yeah, because we're north of the equator. Okay, good. Do you have, or maybe you already have typed in, maybe Carly already has it, San Antonio's latitude? Let's let Carly do it. Carly's on it. Latitude of San Antonio, Texas. I'm expecting it to be in the 30s. I have no idea. Could be, don't say it's 40, but hope not. What do we get? Latitude of San Antonio, Texas. What's that?
Um, 29.4241.
4241. Okay.
I think.
That works. Sounds about right. I said it was about 30. That's what I was expecting. All right. So now that we know that, now this is where everyone else has a calculator. I need to know the difference between those two angles. So I need you to take this 43.1023. I need you to subtract the 29. It's about 13, 14-ish. But I need to know that number really, really accurate.
13.6782.
6782?
Yep.
Nice. Okay, that's degrees. Okay, really, really accurate, that's good. And now we can figure out the distance between the two cities. That's it, that's all we need. An angle, you need the radius, boom. And that's what all Google does. They have those numbers already pre-programmed, as you can tell. And so they're gonna just type it in. So to do the formula here, we're gonna take the what is that, 4,000 miles, that's my radius. We're gonna take it times my angle. Now my angle is 13.6782, and we have to convert it because it has to be in radians. So we have to take it times pi, divide by 180.
0.238.
Okay, and what do we get? So
0.238.
that number is 0.238.
That's what I thought.
Okay, and then we're gonna take it times 4,000. Expecting kind of a big distance.
954.91.
Minus. Makes sense to me. 900 miles to Texas. All right. Now I'm gonna show you, is that accurate? Okay. Before I type it in, I'd like you to write this down before I'm gonna have to erase it so I can show Google up here, and then we're gonna actually type it in so I can show you this cool thing you guys can actually do.
Pull that down.
But if I do, it snaps up and then it tries to hurt me. So I'm just gonna leave it there. So. Okay, so write that down. This is our prediction, what it's gonna be from San Antonio to Garner. That's gonna be my prediction. It's gonna be close. Again, give it a little leeway because that 4,000 miles isn't like perfectly accurate. We're rounding that, so we're gonna be close though. That's roughly about the right number. And that's just the radius of the Earth, by the way. The Earth is really, really big. Okay, so let me turn on the projector here and then we'll get the Google machine working. Alright. Okay, so Garner to San Antonio. Okay. Spring up. Boom. Oops. Probably should screenshot. Alright, here we go. Yeah. Get out of full screen, seriously. Okay, I just need, get out of full screen. How do I do this? Seriously. I can't. It's not even allowing me to. Yeah, I know it's escape. It won't even allow me to hit escape. Oh, okay, here we go. Alright.
Nice.
I had to go in the menu. It wouldn't even let me hit escape, stupid new Mac. Alright. So we're gonna search. Alright, so here's Google Earth. We're gonna do directions. And now what it's gonna do for the directions part, it's gonna give me driving directions, but all I really need to see is like where the buttons are for Garner and San Antonio, so I can put like little markers on it. So I'm gonna type in Garner, Iowa, type in San Antonio, Texas, and yes, I'll zoom in. Or not. It's cool. Okay, whatever, Google
Can you
machine.
make your own markers? Like
Did you
zoom
press
in.
search?
I did. It's not going. Alright, here's what we're gonna do. We're gonna ballpark it. Alright, so there's this little tool up here, if you can see it in this little toolbar. It looks like a ruler, because it is a ruler. And this is the box that pops up on your screen. And, oh, hey, what's it doing? Stop. It's doing it. Now, that's the driving directions. We're going, stop. You're big. Oh my gosh, I'm getting seasick. All right, so what we're gonna do, if you click that little ruler tool, so it actually highlighted my city. So I'm gonna click Garner, and I'm just gonna drag my cursor down to San Antonio. And when I click, it tells me roughly what that number is. So here's what I have. So if you can't see that, that's 971 miles. So 971.67. We're insanely accurate. And as you can tell, this isn't perfectly south. It's close. It's close to being perfectly south from us. What was our number? 954?
954.9.
Yeah. We're only off by like 10, 12, 13, 14 miles. That ain't bad. That's the distance from here to Ventura. You know, that's pretty accurate for just ballparking numbers together, right? So what you're actually seeing there, like this number, that's the curvature of the Earth. That's like the actual flat surface. Now, what they're telling you over here, if you're looking at all these crazy numbers, they're saying it's about 1,000 miles if you drive. Yeah, because you're driving, look at this, you're zigzagging all over the place. Okay? Stop moving, seriously, what are you doing?
Going in.
It's just doing its thing. Stop Google. All right, but the cool number, like this is the concept of what Google uses when it tells you distances between cities. Now, here's the other weird thing that I like, and this is the last topic today. This is what I want to leave you with. North and south on the globe is actually shorter than east and west.
Why?
The Earth is actually being compressed
Oh yeah, like an oval.
like an oval because the Earth is being stretched by the gravity of the sun. So it's pulling us like a football. So we're actually being compressed. So if you actually go east and west, it's actually technically a longer distance, even though like everyone always thinks the Earth is perfectly spherical. It's not. So really the radius of the Earth is really not perfectly accurate because you can't use that radius everywhere. Because if you go east and west, that number's technically a little bit longer. That's why they just say it's 4,000. Because it's, you know, if you went north and south, it might be 3,090. Versus east and west might be 4,000. There's like a difference in a few miles. A few miles not seem like much, but just to give you a concept of this, the whole United States is like 2,700 miles. So if you turn the United States like sideways and stuck it in the earth like a knife, it wouldn't hit the core yet, like the whole thing. So it's big, like it's really big if you think about it. That's a weird concept, but yeah. So it's kind of cool topics. I really like this stuff. I think it's
So
kind of
when
cool.
people try to go to the center of the Earth, they really have to go more than the United States.
Yeah.
Like when they try, oh, it's crazy.
Yeah.
Oh, crazy.
All right. Pretty cool though. I like it.
Insane.